everyone. We are going to continue on in our chapter 16 notes with acid and base strength. The goal of this video is to go through strengths of acid and bases, calculating pH, calculating POH, calculating maybe the hydrogen concentration or hydroxide concentration given pH or given POH. And we also want to talk about K sub A, which is going to be the dissociation constant for acids, and specifically weak acids. So let's go through first and start talking about acid and base strength. So we know that there are 7 strong acids. You were asked to memorize those a few chapters ago. We know that there are 8 strong bases. Again, you were asked to memorize those a few chapters ago. So if we look at this chart, here, I see that for acids, I have strong acids that are more up here. I have several weak acids that are listed here in the middle. And then we have a category that we're going to call negligible acidity. Ultimately, what that means is, these really won't dissociate in water. So because they don't dissociate in water, their acidity, we would say, is just negligible. Now, if I'm looking as I go from the bottom to the top, then we are increasing in acid strength. So let's look over here to the base side. If I look on my base side, I'm starting off at the top of this list with negligible basicity, which means that these, when they're not really going to dissolve in water to give us a base. Then we're going to follow by weak bases, and then we're going to follow into strong bases. So there's a relationship between acid strength and base strength, and that is, if I have a stronger acid, then the base is probably going to be very weak. If I have a strong base, then that should be paired, or they usually are paired, with pretty weak or negligible acids. So strong acids are something that we would say would be completely dissociated in water. So if I'm writing that reaction out, am I going to draw a full arrow, or am I going to draw the double arrow, meaning that it's an equilibrium reaction? You're going to draw the one single full arrow, and that's because it's a complete reaction. They're completely dissociating into their ions, and they're not going to come back together to form the acid again. So strong acids are completely dissociating. When we draw the reaction or write the reaction, it's a full arrow. So strong acids have conjugate bases that are very weak. Weak acids are only going to dissociate partially in water. So because they only dissociate partially in water, that's where for weak acids we're going to be drawing that double arrow. So we're going to have an equilibrium reaction when we're talking about weak acids. So I'm going to have double arrow for this one, but then a full single arrow for the strong acids. For weak acids, their conjugate bases, weak acids have conjugate bases that are also weak. So weak acids are right here. They're going to produce pretty weak acids. Strong acids are going to produce very, very, very weak bases if they, because it's negligible basicity. And if I had a strong base, their conjugate acid is going to be very, very, very weak as well. Okay, so substances with negligible acidity do not dissociate in water. Because of that, we say that their conjugate bases are very, very strong. So we've already talked about that. If I go to this reaction here, we have hydrochloric acid. And is that a strong acid, or would that be a weak acid? Be strong acid. That's one of those 7 strong acids that we need to know. So HCl, strong acid, reacting with water. If this is a strong acid, that means water has to be acting as the base. So if I know that HCl is the acid, I know that water is the base. I also know I could identify conjugate acid, or I could identify conjugate base. So remember that we said that the conjugate acid would be what would be left over after the base accepts the hydrogen from the acid. So water is the base. It's going to accept a hydrogen ion from HCl, giving us then hydronium ion. So I'm going to call that Ca, or the conjugate acid. then my conjugate base is going to be what's left over after HCl donates that H plus ion. So in that case, once this is gone, I'm going to be left with Cl minus, so this must be my conjugate base. Now on the last slides we said that a strong acid should give us a very weak conjugate base, or we should have a pretty weak conjugate base for that. So here's my strong acid, I have HCl. If we go back and look at that chart, HCl, one of the strongest acids. If I go back and look at my conjugate base that I made was Cl minus. So according to what we just said, a strong acid should make a very, very weak conjugate base. And does it do that? Yes, it does. Cl minus. So strong acid makes very weak conjugate base. Okay, now if we're thinking about equilibrium, so ultimately we know from last chapter we have Le Chatelier's principle, which tells us that equilibrium will shift in the direction of some type of stressor. So in any acid and base reaction, the equilibrium will always favor the reaction that moves the proton to the stronger base. So this is true for all acid-base reactions. So I want to always have equilibrium on the side that's favoring the reaction that moves the proton to the stronger base. Well, water is going to be a stronger base than the conjugate base that we made on this side, Cl minus. So because water is a stronger base than Cl minus, the conjugate base, the equilibrium is going to lie very far to the right, meaning that my K is going to be much greater than 1. Let's say that we look at more of a weak, let's say we look at a weak acid or a stronger base. I have acetic acid here. That's a weak acid. It's not one of my 7 strong, so I have acid here. This is going to act as a base, and I know that if this was the base, the conjugate acid is going to be it's going to be the base that's accepted a hydrogen ion, so hydronium is going to be my conjugate acid. That means that acetate ion is going to be my conjugate base. If I go back and look at that first slide that has the table, I know that acetate, CH3, C2H3O2 minus, is a stronger base than water. Because acetate is a stronger base than water, the equilibrium is going to favor the left side. So how does this make sense? Why is it that it says equilibrium is going to favor the reaction that moves the proton to the stronger base? We just said that acetate is the stronger base. So then why does equilibrium favor then the left side? So if H2O is, if our acetate is stronger, then I'm going to have equilibrium. Ultimately, I'm going to be making quite a bit of this because the reaction is favoring this side. And if the reaction is favoring this side, I'm going to make more of these. But that's a problem because I need equilibrium and I need those rates to be equal to one another. So if my reaction's already falling over here, I'm going to have to shift the equilibrium over to the left side so that way I can make more of this, thus to make more of this over here. So I want those rates to be the same. That's the goal when we're talking about equilibrium. So wherever your strong acid lies, if it lies on the product side, then that means that equilibrium is going to have to shift over to the left side, or we're going to say that it favors. That just means that we have to shift because I need more of this then to make this stronger base. This is what I want. It says that the equilibrium favors where the proton, the reaction that moves the proton to the stronger base. So the proton is being moved here to the stronger base here. So I need to make this. That's my goal. Meaning that I need more of this to make this. That's why equilibrium is going to favor this side. So let's do a couple of examples here. Let's say that we have HSO4 and we have CO3 2 minus. and those are going to react to produce bicarbonate and sulfate ion. So let's just go through and label what this is. So this would be carbonate, would be my base. HSO4 would be the acid. And I know that SO4 2- would be my conjugate base. And then bicarbonate would be my conjugate acid. Okay, so if I look at my chart, like we said on that first slide, I know that carbonate has to be the stronger base if I compare carbonate and sulfate. And since carbonate is the stronger base, that means that my equilibrium is going to favor this side. I want to make more of these so that way I can produce this stronger base. So I would say, because we're asking here whether the equilibrium lies to the left or the right. So I would say equilibrium lies to the right. I want more of this to make that strong base. Let's look at the next one. On the next one we have HPO4 2-, that's the acid. Water's going to be the base. Nope, lied. Just kidding. Say, that doesn't make sense. Acid, base. Okay, if H2O is the acid, then that means that my conjugate base that I'm making is going to have that hydrogen ion gone, so OH has to be my conjugate base. And H2PO4 has to be my conjugate acid because it gained that. So in this case, I'm going to compare my bases. I have HPO4 2-, and I have OH-. So if I'm comparing HPO4 2- and OH-, is the stronger base between the two. Because OH is the stronger base, equilibrium is going to have to lie towards the left. Because that means I need to make more of this so I can make that strong base. That's the goal. So this reaction, equilibrium lies to the left. My last reaction, I have NH4+ and OH-. NH4+ will be my acid, OH- will be my base. Then that means that NH3 has to be my conjugate base, and that means that H2O has to be my conjugate acid. So I'm comparing OH- and NH3. OH- is a much stronger base than NH3. So because of that, that means that my equilibrium is going to have to shift towards the right. Because I need to make more of this so that way, ultimately, I can get more of this stronger base. Okay. So a long time ago, and in a long time ago I mean last year, we talked about autoionization of water. I think 4th bell we got to this, 7th bell we got to this like a little bit. So in autoionization of water, we know that water is amphoteric, meaning that it can act like an acid or it could act like a base. So because it has properties of both, in pure water, a couple molecules in water could act like an acid. At the same time that those molecules can also, or some of those molecules can act like a base. So because of this, in pure water, we can have an acid-base reaction between two water molecules. So I could have H2O reacting with H2O. So let's say that this one's going to be the acid, and let's say this one's going to be the base. And in this situation, if I have one acting as the acid, one acting as the base, we're going to make hydroxide ion, and we're going to make hydronium ion. Those will be our products of this autoionization. So let's keep going kind of with that train of thought. It's an equilibrium process, meaning that if I react the water that's acting as an acid with the water that's acting like a base, and I make hydroxide ion and I make hydronium ion, ultimately these two can then react together to form water again. So this equilibrium expression that we write, so we said H2O plus H2O makes hydroxide and hydronium. So when we write the equilibrium expression, remember that we do products over reactants. So I have OH- times H3O plus over, I have two H2O molecules here and they're both liquids. I will not write those in my equilibrium constant because ultimately the two water molecules are similar. I know we said in that one video that if you have two liquids, you should include them then, but it's the same molecule. Or it's the same type of molecule. I just have two H2Os that are liquid. So ultimately, I don't care about those. My equilibrium constant for autoionization, I just care about hydroxide and hydronium. So our equilibrium constant is going to be hydronium ion times hydroxide ion, Kc, because we're talking about concentrations. Now, we're going to change this subscript from C here in a minute to a W, and that's because when I multiply these two together, I should get an actual number afterward, and that number is what we call Kw. Kw is 1 times 10 to the negative 14th, and we call that the ion product constant for water. So this is happening when we have an autoionization reaction in water, and that happens specifically at 25 degrees Celsius. So if it's not at 25 degrees Celsius, this number will be different. But we like to assume that it's all happening at 25 degrees Celsius, so usually you should be fine. So this then, we're going to say equals 1.0 times 10 to the negative 14th. Okay, pH is defined as a negative base log, negative base 10, I should say log, and that's for the concentration of the hydronium ion. So this one, you're going to have to know. I'm going to take my concentration of H3O plus, take the negative log of that, and I'm going to get the pH. We can also talk about something with pOH. I think we'll get there in just a second. We just said that in pure water, Kw is equal to, or we said before, Kc, the equilibrium constant based on concentration, is equal to hydronium concentration times hydroxide concentration. But these two things are going to be equal to 1 times 10 to the negative 14th. In pure water, if we're thinking about something that is neutral, we know H3O plus and the concentration of hydroxide should be equal to one another. So if I have 1 times 10 to the negative 14th, and I'm thinking about a pH of 7, because we know pH of 7 is where on our acid-base scale it's neutral. I need these two to equal one another, but I need their products to equal 1 times 10 to the negative 14th. So if that's true and I'm at a pH of 7, then this is going to have to be 1.0 times 10 to the negative 7th, and this is going to have to be 1.0 times 10 to the negative 7th. So when we're talking about neutral pH, these two concentrations must be equal. This has to be 1.0 times 10 to the negative 7th then for both of these concentrations. If that's true, if I plug for pH equals a negative log of this concentration, 1.0 times 10 to the negative 7th. If I take the negative log of this, guess what? pH is going to equal 7. And we just showed it up here. Awesome. Okay, so an acid has a higher hydronium concentration than pure water, and if that's true, pH is going to be less than 7. If a base has a lower hydronium concentration than pure water, its pH is going to be greater than 7. So on our pH scale, it goes from 0 to 14. This should also make sense because if I took the negative log of the Kw, the ion product constant for water, then that would give me a pH of 14. So our scale goes from 0 to 14. Okay, and then this table is just showing relationships between hydrogen concentration, which is the same thing, analogous to hydronium concentration, or also hydroxide concentration, because we have pH, but we could also have something called pOH, and that would be finding the log scale based on the concentration of hydroxide instead of finding the concentration based on hydrogen. So here's my pH scale. They give us a couple different examples here of acid strength based on hydrogen concentration. They also give us some examples more of bases as we go with a stronger basicity. So we can see that stomach acid, you have quite a bit of hydrochloric acid in your stomach, and that's going to fall at a pH of 1. Lemon juice, soda, cola, pH of around 2. If you drink coffee, you're a big coffee drinker, we have a pH of 5. A lot of rain is acidic, so rain would be in between 5 and 6. We look more at the base side. Bleach is going to fall into a range, if we're thinking about pH, of about 12. So because that pH is greater than 7, that's where we're getting those base numbers here. Or we can think about it as POH in terms of hydroxide concentration. So in that case, it would be the opposite. So the other P scale is what we just said, POH. And all that means is, instead of taking the negative log of the concentration of hydrogen, we're going to take the negative log of the concentration of hydroxide. So it's no different in just that you're taking hydroxide concentration instead of hydrogen, or hydronium. So let's do an example. Let's say that you have a hydroxide concentration, so we have an OH concentration of, let's do 0.01 molar. And I'm asking you to calculate the pH. How would I find the pH? So I know that Kw equals the concentration of hydronium, or hydrogen, times the concentration of hydroxide. And I also know that that equals a constant. I know that equals 1 times 10 to the negative 14th. Well, I know this is 0.01, so I have this. So I could say H3O plus times 0.010 molar equals 1 times 10 to the negative 14th. So if I took my 1 times 10 to the negative 14th and I divide it by 0.01, we're going to get a concentration for hydrogen, H3O plus, should equal 1.0 times 10 to the negative 12. And if I take the negative log of this, that will give me my pH. So if I took the negative log of 1.0 times 10 to the negative 12, my pH should be 12. We also could have done this another way. If I knew the hydronium, or if I knew the hydroxide concentration is 0.01, and I took the negative log of that, it would have given me a POH of 2. And POH plus pH equals 14. Because we said that our acid-base scale is going to be between 0 and 14, and we know that the concentrations of these two, of their products, equals 1 times 10 to the negative 14th. So the POH plus the pH has to then equal 14. So if I just took the negative log of my hydroxide concentration, 0.01 molar, that's going to give me a POH of 2. And I know I could find pH then, because I know that that plus the pH is equal to 14, thus meaning the pH has to be 12, and that's what we found here. This way may be shorter to do. If you're asked this on a question for FRQ, they probably would prefer to see this. This way is not wrong, as long as you show all of your work in the process, because they just care about the chemistry. Okay, so what we just did on this last example, because I know that these two of the product equals Kw, which equals 1 times 10 to the negative 14th, I know that if I took the negative log of both of them, it's going to give me 14. So I could say pH plus POH is just going to be equal to 14. Okay, so how do we measure pH? You actually worked on measuring some pH yesterday, even though we were doing a titration. But we used an acid-base indicator to kind of measure pH, and that indicator that you used yesterday was called phenolphthalein. So we'll get more into titration, probably more in chapter 17, which we're just going to add on to this chapter because it's pretty much just all about acids and bases. But if we wanted to use a less accurate route for measuring pH, we're going to use litmus paper. And if litmus paper turns red, then typically, if red paper turns blue, we should say, then we know that that's telling us it's more basic. If blue paper turns red, then that means we're more on the acidic side. So if you have red litmus paper and it stays red, then it's an acid. If you have red litmus paper and it turns blue, then it's basic. If you have blue litmus paper and it stays blue, that means it's a base. If you have blue litmus paper and it turns red, then that means that you have an acid. We also have a more fancy pH paper or litmus paper now, and that's where they kind of give us a color scale. So we also have these different color indicators or acid-base indicators. So yesterday we used an acid-base indicator called phenolphthalein. Ultimately, phenolphthalein works within a range, so once you got that nice pink color, the pH then of that titrant was probably in between 9.5 and 10. So our goal when we use a color and acid-base indicator is that, especially for titration, we're trying to find something called the equivalence point. And an equivalence point is where we have equal concentrations for the acid and the base. So it's like right on this edge where my concentrations are equal, so thus we call it the equivalence point. You can see that there are different color indicators based on different pH ranges. So thymol blue, methyl orange, and methyl red are very similar in the fact that they start off red and then they'll turn yellow once they have reached an equivalence point. So these three, it just depends on what kind of pH that you want. If we want to look at totally different colors, methyl violet would give us a yellow and violet, but like phenolphthalein, like we saw yesterday, starts off colorless and then will turn pink once it's reached its equivalence point. If we want a more accurate measurement for acids and bases, then we're going to use something called a pH meter. And ultimately, we just stick an electrode. So the electrode is right here. This electrode is attached where we can measure the pH meter just simply by using voltages. We're going to be using these this week in class. Okay, we said that we need to know our strong acids. There are 7. Those 7 are listed right here for you in case we forgot. A strong acid, by definition, means that it's a strong electrolyte. So that means that it exists totally as ions in an aqueous solution. So these will fully break or dissociate apart into their ions. So note the single arrow, because this reaction is only going to be a forward reaction. These two aren't going to come back together to make more HNO3. For monoprotic acids, this is really important. For monoprotic acids, the hydronium concentration is simply equal to the concentration of that acid. So if I have, for example, HNO3, HNO3 is just going to be equal to the concentration of whatever acid I have in a sample. So it's only true for monoprotic. What does monoprotic mean? Monoprotic means I have one hydrogen. But remember, it's not just any hydrogen. For acids, when they dissociate, they need to be ionizable hydrogens. Ionizable hydrogens. Remember that an ionizable hydrogen is something that can dissociate when it's in water to form a hydrogen ion. So in HNO3, the hydrogen ion here can break apart from the nitrogen, and it could leave me with HNO3 and H+. So this does have an ionizable hydrogen. There's monoprotic strong acids. We also have one diprotic strong acid, and that's sulfuric acid. So we'll get to polyprotic acids in a little bit. Strong bases, we already know that those are the alkali metals with hydroxide, and then 3 of the alkaline earth metals, calcium, strontium, and barium with hydroxide. Again, these are going to dissociate completely, so we're going to use that one single strong arrow. If we talk about weaker acids, though, A generalized acid dissociation is, let's say, HA, so just some fake acid, plus water is going to produce A minus and H3O plus. So if I want to write an equilibrium expression for this, it's, again, products over reactants. So here are my products, so the product of the products over my reactants. Well, since water is in liquid form, I'm not going to include that, remember, in my equilibrium expression. So we're just going to have H3O plus times A minus, so the product of the products, over the reactants. We call this equilibrium constant, we're not going to call it Kc, even though it's based on concentrations, we're going to call it K sub A, because that's going to tell us that it's the acid dissociation constant. Ultimately, the greater the value of Ka, the stronger the acid we have. So thinking about most acids, there are only 7 strong acids that we even have to memorize or have to know. The rest of those acids are considered to be weak acids. So most acidic substances are weak, and they're only going to be able to partially ionize. So because of these weak acids, that's why we're having to write these equilibrium constants for ionization. And it's just because it helps us know to the extent of a weak acid being able to dissociate in water. So that's why we're writing the Kas. So the greater the value of Ka, the stronger the value. Because if we go back and look here, the greater Ka is, that means that this product side has to be more heavy than the reactant side. So if I have more of this, that means I have more dissociated ions. So if these concentrations are larger, meaning I have more of these, it's going to be a stronger acid, because then that means it's dissociating into more ions. So that's why we get the greater the value of Ka, the stronger the acid. So this is just a chart showing some different weak acids here. They've given us values of Ka, and they also just showed the conjugate base. Okay, so let's just look very quickly at one of these examples. So this says, let's calculate Ka, an acid dissociation constant from pH. The pH of a 0.1 molar solution of formic acid, which is HCOOH, at 25 degrees Celsius is 2.38. So I know that pH here equals 2.38. I want to calculate Ka for formic acid at this temperature. The first thing that you need to do, if they don't give you a reaction, you write a reaction, because there's no way that we will ever get to this step if we don't know, first of all, how to write it to begin with. So I have formic acid, HCOOH, and that formic acid is in water, so I'm going to say plus H2O. And that's going to dissociate into H3O plus, hydronium ion, and HCOO. Or we could say COOH, whichever one. They wrote it as HCOO, but it doesn't matter. Either way. So now that I have written my reaction, it's easier than, I know that this is aqueous, water is a liquid, and if they're ions, they have to be in aqueous form. I know that this is aqueous because acids are dissolved in water, thus giving us aqueous here. So if I write my Ka, I have my products, so the product of the products, H3O plus HCOO minus, over my reactant. I'm not including water because it's a liquid. So always write the reaction first. So any step, reaction first. Then we're going to always write the equilibrium expression for Ka. So this is calculating Ka from pH. So first step, reaction. Second step, Ka. Next, to calculate Ka, I need to know the equilibrium concentration. I need to know the equilibrium concentration of a couple different things. So first of all, they told me in the problem that we're at a pH of 2.38. So this was given to me. So I could find hydronium concentration because I know the pH is at 2.38. This says that H3O plus concentration is the same as HCOO minus concentration. How do I know that? I know that because if I'm looking at my reaction, when this breaks apart into ions, I'm going to be getting 1 mole of this for every 1 mole of this. It's going to be breaking apart into a hydrogen ion at the same rate it's going to break up into an HCOO minus ion. So because these two ions, I'm getting a 1-to-1 ratio of ions, their concentrations have to be the same. So first of all, I could say pH is equal to a negative log of hydronium concentration. I know pH is 2.38. I could find then the concentration of this. So if I do, if I look at that, this becomes, let's take the negative over here to this side. So a negative 2.38, I'm going to end up taking 10 to then this particular power, and then that's going to equal my hydrogen concentration. So if I do that in my calculator, we're going to get hydronium concentration is equal to 4.2 times 10 to the negative third. So that would be equal to my hydronium. But that means it's also equal to the other ion because, let's go back, when this breaks apart, it's dissociating into one hydronium ion or H plus ion and then one ion of COOH minus or HCOO minus. So because it's a 1-to-1, the concentration of this has to equal the concentration of this. So that's why I can say that they're equal. So I know now the concentration of H3O plus, I know the concentration of HCOO minus. I don't know the equilibrium concentration of this. I do know initially it starts off at 0.10 molar, but I don't know what it is at equilibrium. So let's use an ice box. So I know initially I'm starting off with this molarity of formic acid. And that means I'm not going to have anything initially of my products. If I think about how they're changing, so ultimately we know, I could say this is plus X, minus X. I can say that because of my reaction here. It's all 1-to-1. I know that these two are going to be increasing in concentration because we started from 0. This must be decreasing in concentration because it's dissociating to make those things. So that's why I can say this is minus X, these would be positive X. Well, we just calculated that the concentration for H3O plus has to be 4.2 times 10 to the negative third at equilibrium. And we said that hydronium concentration or for H3O plus concentration has to equal the HCOO minus concentration because for every hydrogen ion I get, I'm going to get this ion, so this also has to equal 4.2 times 10 to the negative third. So if that means that X has to equal 4.2 times 10 to the negative third. So if X equals this, I can plug in 0.10 minus X has to equal my equilibrium concentration here. Well, I know X is this. So 0.10 minus 4.2 times 10 to the negative third. If I do that, you should get something that's like 0.0958. But if I'm looking at that, ultimately, isn't that close to just 0.10? So because that's rounded to 0.10, I'm pretty much just going to leave this as 0.10. So if you keep going on your slides, I kind of filled these in, I think, already for you. I did. Okay, so now that we know all of our concentrations at equilibrium, I know this one for hydronium, I know this one for HCl minus, I know this one for my formic acid. So if I take the product of the products, divide it by the reactant, I get my Ka to be 1.8 times 10 to the negative fourth. And this should, this is actually a pretty reasonable acid dissociation constant for a weak acid, because usually Ka's should fall within 10 to the negative second, and then 10 to the negative 10th. So if you're in between this range, that's a good Ka. Okay, so guys, we're going to start here on Monday. So I will see you guys on Monday. If you have any questions over this, let me know. Post on the blog or email me, whichever works. And we're going to do a lot of practice with Kas. So have a really good weekend, guys. Bye.